Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into the fascinating world of GenAI-powered inference. It's a broad topic, but I think we can really drill down into some of the key advancements and perhaps more importantly, some of the limitations.
Excited to be here. Gen AI inference is such a hot topic. It feels like every day there's a new breakthrough or application being announced. Just yesterday, I saw a demo of an AI inferring complex causal relationships from a simple video. Absolutely mind-blowing.
I'm a bit more cautious in my enthusiasm. While the demos are impressive, I always wonder how much of it is just clever engineering versus genuine understanding. I mean, can these systems really infer, or are they just regurgitating patterns they've seen in their training data?
That's exactly my concern. It's like, are we building truly intelligent systems or just really sophisticated parrots? The ability to generalize beyond the training data, to understand the why behind the what, that's what I think is crucial for real inference.
That's a perfect starting point. The Harvard/MIT study that came out recently really underscores this issue. They found that even the most advanced LLMs often lack what they call an internal world model. They can generate text that sounds coherent and even insightful, but they don't actually seem to understand the underlying concepts or relationships. It is a statistical model at the end of the day. This also affects reasoning, which affects inference.
Yeah, I saw that study. Disappointing, but not entirely surprising. I think it's a temporary setback, though. We're throwing so much data and compute at these models, it's only a matter of time before they start to develop something resembling an internal world model. It's all about scale, in my opinion. The transformers were a big breakthrough, and I'm sure there are more architectural innovations on the horizon.
I'm not so sure it's just about scale. I think there's a fundamental limitation to the deep learning approach. These models are essentially black boxes. We don't really understand how they work, and we have very little control over what they learn. I think we need to explore more neuro-symbolic approaches, where we combine the strengths of neural networks with the explainability and reasoning capabilities of symbolic AI.
I agree with you there. It feels like we're trying to brute force our way to AGI with these massive deep learning models. But I think we're missing a crucial ingredient, a way to represent and reason about space and time. I call it spatiotemporal reasoning. These models need to be able to understand how objects move and interact in the world, how cause leads to effect. And I suspect the core algorithm that can do this will need to be able to translate between different coordinate representations.
That's a really interesting point about spatiotemporal reasoning. Think about how a self-driving car navigates a busy street. It's not just recognizing objects, it's predicting their future trajectories, understanding the relationships between them in space and time. Current AI systems struggle with that kind of dynamic, real-world understanding. The ability to build those real-time mental models is really the kicker here.
But self-driving cars are getting better all the time. They are a product of deep learning. The improvements in object detection and path planning are undeniable. It's true that they sometimes make mistakes, but that's just a matter of refining the models and training them on more data. I mean, look at the progress in the last few years. It's exponential.
Yes, and that's great for object detection. But what about when the unexpected happens? A child runs out into the street, or a sudden detour changes the traffic patterns. These are situations that require flexible reasoning and the ability to adapt to unforeseen circumstances. And I'm not convinced that deep learning alone can provide that.
Exactly. It's about understanding the underlying physics of the world, not just recognizing patterns. A self-driving car needs to understand that if it accelerates too quickly on a slippery road, it's going to lose control. That's not just a matter of memorizing examples, it's about understanding the relationship between force, mass, and acceleration. It's about translating between different representations of space and motion.
This makes me think about how the human brain handles sensory input. We don't just passively receive information, we actively construct a model of the world based on our experiences. And that model is constantly being updated and refined. How can we build AI systems that mimic that kind of active perception and model building?
Well, that's what neural networks are trying to do, right? They're learning to extract features and represent information in a hierarchical way. The deeper the network, the more abstract the representations become. And with enough data, these networks can learn to approximate any function, including the function that maps sensory input to an internal world model. You know, I think we are getting close.
But approximate is the key word there. They're approximating, not understanding. And that approximation can break down in unexpected ways. That's why I think we need to incorporate explicit knowledge and reasoning into our AI systems. We need to give them the ability to understand the why behind the what.
And that why often involves understanding spatial relationships and how they change over time. Think about how a chess program works. It doesn't just evaluate the board position, it also considers the possible future moves and their consequences. It's reasoning about the spatial relationships between the pieces and how they will change over time. That is spatiotemporal reasoning.
That brings up a really important point about planning and decision making. It's not enough to just understand the current state of the world. You need to be able to predict the consequences of your actions. And that requires a sophisticated understanding of cause and effect, which again relies on an internal model of the world. How can we design AI systems that can reason about counterfactuals? What if I did this instead of that?
That's where reinforcement learning comes in. It allows AI systems to learn through trial and error by exploring the consequences of their actions. And with the advances in deep reinforcement learning, we're seeing AI systems that can master incredibly complex tasks, like playing Go at a superhuman level. In a closed-world environment, you can infer from action space resulting effect, build a world model, then apply it to other worlds. Not necessarily the same.
But even reinforcement learning has its limitations. It requires a lot of training data, and it can be very sensitive to the reward function. If the reward function isn't carefully designed, the AI system can learn to exploit loopholes and achieve the goal in unintended ways. The old paperclip maximizer thought experiment illustrates this perfectly. An AI designed to maximize paperclip production might end up consuming all the resources on Earth to achieve its goal.
And reinforcement learning often struggles with tasks that require long-term planning or hierarchical decision-making. It's good at learning to react to immediate situations, but it's not so good at planning for the future. This is where being able to translate between different coordinate spaces could really help. Representing goals in different frames of reference could allow for more efficient planning.
Right, so thinking back to the Harvard/MIT study, if LLMs lack this internal world model, does that mean the whole brute force deep learning approach is a dead end? Or is it just a necessary stepping stone? How much of the success of these models is due to the sheer scale of the data, and how much is due to the underlying algorithms?
I definitely don't think it's a dead end. I think it's a very promising avenue, and we're only just scratching the surface. The scale of the data is definitely a factor, but it's not just about quantity, it's also about quality. And the algorithms are constantly improving too. We're seeing new architectures and training techniques that are allowing these models to learn more efficiently and generalize better. More data is always good, though. I agree that we need to learn how to integrate the data and algorithm better so we can train faster.
I think it's a necessary stepping stone, but not sufficient. Deep learning is good at pattern recognition, but it's not good at reasoning or understanding. We need to combine it with other approaches, like symbolic AI, to create truly intelligent systems. I feel like there needs to be some human intuition in the training process, more than the brute force method of pumping more data into the system.
I agree. It's like deep learning is giving us the raw sensory data, but we still need to build the cognitive architecture on top of that. We need to find a way to represent and reason about space and time, to translate between different coordinate systems. That's where I think the real breakthroughs will come.
So if we accept that current LLMs lack an internal world model, what are the implications for their capacity for generalization? Can they truly learn anything, or are they just memorizing and predicting associations? What about the ability to transfer knowledge from one domain to another?
That's a tough question. I think they can learn, but their learning is different from human learning. They're learning statistical relationships, not necessarily causal relationships. And their ability to generalize is limited by the data they've been trained on. But I think we can improve their generalization ability by training them on more diverse data and by developing new training techniques. So I think it is a case of more data and integrating the algos.
I think they're learning to mimic behavior, not to understand it. They're good at generating text that sounds intelligent, but they don't actually understand what they're saying. And their ability to transfer knowledge is very limited. They can learn to translate between languages, but they can't learn to apply the same principles to a new problem domain. I think it's because there is no underlying understanding in what they are building.
It's like they're learning to navigate a maze by memorizing the path, rather than by understanding the underlying structure of the maze. They can follow the path they've been shown, but they can't find their way if the path is changed. To truly generalize, they need to understand the underlying spatial relationships and how they can be transformed. It would be awesome if they could explain the maze in a different way or a different language. And they can't do that right now.
Okay, so if LLMs can't build internal world models, what kind of representation of the world is being learned? Is it merely statistical correlations, or is there some hidden symbolic structure that could be extracted and reasoned about? How can we design algorithms that are explicitly directed towards creating and using such symbolic representations?
I think it's mostly statistical correlations, but I wouldn't rule out the possibility of hidden symbolic structures. Neural networks are very good at extracting patterns from data, and it's possible that they're learning to represent knowledge in a way that we don't fully understand. But I think we can improve their ability to learn symbolic representations by incorporating symbolic AI techniques into their architecture.
I think they're learning a shallow representation of the world, a representation that's based on surface features rather than underlying principles. They're learning to associate words with other words, but they're not learning to understand the meaning of those words. I think we need to design algorithms that are explicitly directed towards creating and using symbolic representations, algorithms that can represent knowledge in a structured and meaningful way.
It's like they're learning to recognize objects by their appearance, rather than by their function or their relationship to other objects. They can recognize a chair, but they don't understand that a chair is something you sit on, or that it's often found in a room with a table. To truly understand the world, they need to be able to represent objects in terms of their properties and relationships and to translate between different representations. Maybe a neuro-symbolic approach can allow for this conversion and abstraction.
So the million-dollar question, what are the most promising research directions in this area? What kind of experiments or theoretical frameworks could help us bridge the gap between statistical pattern recognition and a truly experienced understanding of the world, one that captures causal relationships and underlying dynamics?
I think we need to continue exploring new neural network architectures and training techniques. We need to find ways to make these models more efficient and more generalizable. And we need to train them on even more data, especially data that's designed to challenge their understanding and force them to learn causal relationships. But I also think we need to start exploring new hybrid approaches that combine the strengths of neural networks with the strengths of symbolic AI. It will be a matter of throwing everything at the wall and seeing what sticks.
I think we need to focus on developing more robust and explainable symbolic AI algorithms. We need to find ways to represent knowledge in a structured and meaningful way, and to reason about that knowledge in a way that's transparent and understandable. And we need to find ways to integrate these symbolic AI algorithms with neural networks so that we can leverage the strengths of both approaches. I think there needs to be a better way to integrate external knowledge, or domain expertise, into the deep learning systems.
I think we need to focus on developing algorithms that can represent and reason about space and time. We need to find ways to translate between different coordinate systems and to represent objects in terms of their properties and relationships. And we need to find ways to incorporate these spatial and temporal reasoning abilities into our AI systems. I think this might involve developing a new kind of computational architecture, one that's specifically designed for spatiotemporal reasoning. I am really interested in seeing how this goes, and I feel this is the piece that will bring AGI to fruition.
From my perspective, I think we need a more biologically inspired approach to AI. We need to study how the human brain represents and processes information and to try to mimic those processes in our AI systems. That means looking beyond just the statistical properties of neural networks and delving into the underlying neural pathways and their functions. It means understanding how the brain integrates information from different sensory modalities and how it builds and maintains its internal model of the world. How can neuroscience help to inform AI algos? That is something that I think is super important. It will really help pave the way, and that is why I love this field. This kind of internal model and grounding is important for all intelligent creatures. It feels like we are missing some of the basic concepts in AI.
Yes, and I would add that we need to analyze the correlation between specific architectural changes in deep learning models and observed improvements in various benchmarks. This kind of analysis might reveal crucial insights into what aspects of these models are driving their enhanced performance. Also, you can't neglect the exponential increase in data and computational power available.
I agree with you to an extent. However, the emphasis on raw data volume in deep learning feels like a shortcut. How much data is really necessary for successful neurosymbolic algorithm development? Perhaps the quality and structure of the data matter more than the quantity. The current focus on massive datasets feels like a distraction from the crucial need for more robust, explainable symbolic AI.
I am with you on that. The sheer complexity of translating between different spatial representations feels almost overwhelming. Perhaps we are missing a key underlying mathematical principle that bridges the gap between these different frameworks. This suggests AGI isn't simply about throwing more data at the problem, but understanding and leveraging the underlying structure of the world's representations.
Well, this has been a truly insightful discussion. It's clear that GenAI-powered inference is a complex and multifaceted field, with both tremendous potential and significant challenges. While the current focus on deep learning has yielded impressive results, it's also highlighted the need for a more nuanced and biologically inspired approach, one that integrates symbolic reasoning and spatiotemporal understanding. Thanks everyone for sharing your perspectives.
My pleasure. It's always great to explore these ideas and challenge our assumptions. I am optimistic about the road ahead. More data, more power.
Indeed, I look forward to seeing how the field evolves in the coming years. I remain cautiously optimistic, but hopeful for more robust and explainable AI.
Thanks for having me. I'm excited to see what the future holds for AGI, especially in the realm of spatiotemporal reasoning.